Hello students. Our next series of discussion is on chemical bonding. We are going to discuss ionic bond in this session and then covalent bond in the next. When we think about chemical bonding, the first question that comes to our mind is, why do atoms combine with each other to form a molecule? The driving force behind combination of atoms to form a molecule is stability. Stability of a system is generally associated with the lowering of energy of the system. So, when atoms combine and form a molecule, it means that the resulting molecule is more stable than its individual constituent atoms and has a lower energy as well. The elements of group 18, which are known as noble gases, are known for their inertness. That is, noble gas atoms show very little tendency to react with other atoms. This lack of reactivity is attributed to the fact that noble gas atoms are already stable and have low energy, which cannot be further lowered by the formation of new molecules. Why is it so? Low energy of noble gas atoms is associated with their having outermost shell which is completely filled with electrons. This arrangement is also known as noble gas structure. Let us see what makes a bond. Normally, outermost electrons of an atom participate in bond formation. So, outermost electrons of two or more atoms are involved in formation of a bond which results in a molecule. After bond formation, each atom has a more stable configuration than what it previously had. Also, the most stable electronic arrangement is a noble gas structure, and many atoms attain this structure after bond formation. Note, however, that transition elements form molecules which are less stable than this arrangement. The atoms can attain a stable electronic configuration, that is the noble gas structure, in following one of the three ways. First is by losing electrons, second by gaining electrons, and the third is by sharing electrons. Now, based on which method they use to attain a noble gas configuration, the elements can be divided into three types. First is the electropositive elements. These are the elements which can easily furnish or lose an electron. The second type are the electronegative elements. These are the elements which can easily accept an electron. And the third type are those elements which have very little tendency to gain or lose electrons. This table illustrates the type of bond formed when atoms of different kind of elements combine. For example, when an atom of electropositive element combines with another atom of electronegative element, ionic bond is formed. When an atom of electronegative element combines with another atom of electronegative element, covalent bond is formed. And when atom of an electropositive element combines with another atom of an electropositive element, metallic bond is formed. Ionic bonding involves complete transfer of one or more electrons from one atom to another atom. Covalent bonding involves sharing of one or more electrons between two atoms. And in metallic bonding, valence electrons are free to move throughout the crystal. We must bear in mind that the above three types of bonds are idealized in the sense that generally molecules show character of one or more bond types. For example, lithium fluoride is an ionic compound, but it is also soluble in alcohol, which suggests that it possesses a little covalent character as well. Very few bonds are purely ionic, covalent, or metallic. Most are intermediate between the three main types. Now let's start with ionic bonding. Ionic bonds are formed when electropositive elements react with electronegative elements. Let's consider the case of sodium chloride, that is NaCl. The electronic configuration of sodium is 1s2, 2s2, 2p6, 3s1. We observe that the first and the second shell are full and the third shell has one electron. When sodium atom reacts, it does so in such a way so as to attain noble gas structure. If sodium loses one electron, the resultant electronic configuration will be 1s2, 2s2, 2p6. Here, the outermost shell, which is second shell, is completely filled. Also note that this is the way electrons are configured in neon. So by losing one electron, sodium attains a noble gas structure which is more stable. Also, in doing so, sodium acquires a net positive charge and is now called sodium ion. So as you can see in the equation, sodium, which gives sodium ion plus an electron. The positive charge arises because sodium nucleus has 11 positively charged protons, each having a unit positive charge. Whereas after losing one electron as in its ion, it now has only 10 electrons, each having a unit negative charge. So the net charge which remains on sodium ion is 11 minus 10, that is 1 positive charge. Now let's come to chlorine atom. The electronic configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. This is only one electron short of noble gas configuration of argon, which is 1s2, 2s2, 2p6, 3s2, 3p6. So when chlorine reacts, it tends to gain one electron in order to attain noble gas structure. So as we can see in the equation, Cl, that is chlorine atom, plus an electron will give Cl minus, that is chloride ion. So when sodium and chlorine react together, the outer electron of sodium ion, that is this 3s1 electron, is transferred to chlorine atoms, forming sodium ion and chloride ion. These two oppositely charged ions are now held together by electrostatic attraction in a crystalline lattice. This is what we called ionic bond formation. As we can see in the figure, sodium atom contains one electron more than the noble gas configuration. If it loses its outermost electron, it will have 8 electrons in its outermost orbit. Similarly, chlorine atom, which has 7 electrons in its outermost orbit, consists of 1 electron less than the noble gas configuration. Therefore, sodium atom will tend to lose an electron to form sodium plus ion, and chlorine atom will tend to gain an electron to form chloride ion. The two oppositely charged ions will be attracted by electrostatic force of attraction and will form an ionic bond to form ionic sodium chloride. Now consider the case of calcium chloride, that is CaCl2. As we can see in the configuration of calcium, that calcium atom has 2 electrons in its outermost shell, that is these 4s2 electrons. And after losing these 2 electrons, it can achieve noble gas structure. Whereas chlorine atom, as we have already discussed, is 1 electron short to attain noble gas structure. So calcium atom loses its 2 electrons, and each of the 2 chlorine atom accepts 1 electron to form 2 chloride ions. Now these oppositely charged ions, that is 1 bivalent calcium ion and 2 chloride ions, are held together by electrostatic force of attraction in a crystalline lattice. The example of calcium chloride is quite similar to that of sodium chloride. Calcium atom has 2 electrons extra to the noble gas configuration, so it will tend to lose 2 electrons to form a dipositive calcium ion. The chlorine atom, which has 7 electrons in its outermost orbit, will tend to gain 1 more electron to have 8 valence electrons. The calcium ion and the 2 chloride ion will attract each other through electrostatic force of attraction and will form ionic calcium chloride. This table illustrates the type of ionic compounds formed when electropositive and electronegative elements belonging to different groups of the periodic table react with each other. As we can see that the electropositive elements belong to the groups 1st A, 2nd A and 3rd A, and the electronegative elements belong to the group 5th A, 6th A and 7th A. The elements of 1st A form unipositive ions, those of 2nd A form dipositive ions, and those of 3rd A form tripositive ion. Similarly, the electronegative elements of 5th A form trinegative ions, those of 6th A form dinegative ions, and those of 7th A form uninegative ions. These are the various general formula which will be obtained when these elements combine with each other. Let's take the examples one by one. The first is NaCl. Sodium belongs to the group first A, and so it will form sodium plus ion, and chlorine belongs to the group 7th A, so it will form Cl minus, that is chloride ion. Together they combine to form NaCl, that is sodium chloride. Similarly, the next example is CaCl2. Ca belongs to the group 2nd A, so it will form Ca2 plus ions, and Cl, that is chlorine again, belongs to the group 7th A, so it will form Cl minus ion. And together they will combine to form CaCl2, in which 1 calcium ion and 2 chloride ions are combined. Third example is gallium fluoride. Gallium belongs to group 3rd A, so it will form Ga plus 3 ion, and fluoride, just like chlorine, fluorine also belongs to the 7th A group, so it will form chloride ion, which is F minus. Together they combine to form GaF3. Our next example is Na2O. We have already discussed sodium, that is Na, which belongs to the group 1st A. It forms Na plus ion, and oxygen forms O2 minus ion. It belongs to the group 6th A. So 2 Na plus and 1 O2 minus ion combine to form Na2O. The next is MgO, magnesium oxide. Magnesium belongs to the group 2nd A. It will form Mg2 plus ion. And oxygen, just like the earlier example, will form O2 minus ion, and together they combine to form MgO. Next example is alumina, that is Al2O3, aluminum oxide. Aluminium belongs to the group 3rd A, so it will form Al3 plus ion, and oxygen, as earlier, will form O2 minus ion. 2 Al3 plus ions and 3 O2 minus ion will combine to form Al2O3. Next example, lithium nitride, Li3N, in which lithium belongs to group 1A and nitrogen to 5th A. Lithium will form Li plus ion and nitrogen will form N3 minus ion, and together they form Li3N. Similarly, the next example, Ca3P2, in which Ca belonging to 2nd A will form Ca2 plus ion, and phosphorus belonging to 5th A will form P3 minus ion. 3 Ca2 plus ions and 2 P3 minus ion combine to form Ca3P2. The last example is AlP, aluminium phosphide, in which aluminum belonging to 3rd A group will form Al3 plus ion, and phosphorus belonging to 5th A group will form P3 minus ion. Together they form AlP. Now let us have a look at some of the most common properties of ionic compounds, which are generally shown by all ionic compounds without any exception. The first one is ion formation. The atoms involved in ionic bonding lose or gain electrons to form charged ions. Positively charged ions are called cations and negatively charged ions are called anions. Cations and anions are more stable than the parent atoms because they have completely filled outermost shell. The second property is the structure of ionic compounds. Ionic compounds are typically solid and made up of cations and anions, which are arranged in a regular way in a lattice. The attraction between ions is electrostatic and is given by the formula F is equal to Z1 Z2 E square divided by dr square. Here F is the force of attraction, Z1 and Z2 are the charges on the ion, small e is the electronic charge, capital D is the dielectric constant of the medium, and small r is the bond length or interionic distance. The attraction is non-directional, which means the force of attraction extends equally in all directions. The next property of the ionic compounds is the melting and boiling point. Owing to the lattice structure, which requires considerable amount of energy to get broken, melting point and boiling point of ionic compounds are quite high. Next comes the solubility. Ionic compounds are usually soluble in polar solvents like water, which have high dielectric constants. One thumb rule for solubility is like dissolves like, which implicates that ionic compounds are soluble in ionic solvents or polar solvents. We'll discuss the solubility of ionic compounds in detail. When an ionic compound gets dissolved in a solvent, its ions, that is cations as well as anions, break free from its crystal lattice and get solvated in the solution. Now, breaking of the crystal lattice to release the ions requires energy, which is equal to the lattice energy of the crystal, and solvated ions in the solution evolve energy. A given ionic compound will be soluble in a given solvent if the enthalpy of solvation is greater than the lattice energy of that compound. We'll discuss these points one by one in detail. Let's take the example of an ionic compound Mx, which is composed of M plus cations and X minus anions. It is dissolved in a solvent, let's say water. So, the ionic compound M plus X minus will disintegrate into M plus ions and X minus ions, which will eventually get solvated, or when we use water as a solvent, we can say that they'll get hydrated. The enthalpy of this reaction will be equal to the enthalpy of solvation. We can define molar enthalpy of solvation, which is denoted by delta H solvation, as the energy that is released when 1 mole of ionic solid is dissolved in a solvent. If the value of delta H solvation is negative, that means energy is evolved or the reaction is exothermic, and it suggests that the ionic compound is soluble in the given solvent. Let's consider another equation in which gaseous cations and anion instead of the solid ionic compound is dissolved in water, and the anions and the cations get solvated or say hydrated. In this case, the enthalpy of reaction will be equal to the enthalpy of hydration. We can define molar enthalpy of hydration, which is denoted by delta H hydration, as the energy which is released when 1 mole of ions is dissolved in large amount of water, forming a solution of infinite dilution. That is, as compared to the volume of water, the ions will be in very low quantity. Consider another equation in which the solid ionic compound disintegrates into its ions. In this reaction, the enthalpy of reaction will be equal to the lattice energy, which is denoted by U. Lattice energy can be defined as the energy evolved when 1 gram mole of a solid ionic compound is formed by the combination of its gaseous ions. So we can say that if these ions combine to form this solid ionic compound, energy equal to the lattice energy will be required in the formation. Vice versa, we can say that when this ionic compound will break down into its ions, energy equal to lattice energy will be released. Now, if you remember, this was the first equation that we discussed. That was equation A. This is equation B, and this is equation C. Now, if we add equation B and equation C, we obtain equation A. So we can say that delta H solvation will be equal to the sum of delta H hydration and U, where delta H solvation depicts enthalpy of solvation, delta H hydration stands for the enthalpy of hydration, and U is the lattice energy. Now, there are certain points we must always keep in our mind. First of all, ionic size, whether it's the size of cation or anion, it increases on moving down a group. Second is, the enthalpy of hydration is inversely proportional to the size of the ion. And the third point is, the lattice energy is also inversely proportional to the ionic size. Now let us see how these points are going to affect the trends of solubility that we generally observe. These are the two important conclusions which we can draw from the points we discussed. First of all, if the anion and cation are of comparable size, that is, there is not a very big difference between the sizes of an anion and cation, then on moving down a group, as the size increases, the lattice energy will decrease. The hydration energy will also decrease along with increase in size, but the decrease in lattice energy will be much more as compared to the decrease in hydration energy, and therefore the solubility will increase. The second conclusion is that if the anion is large compared to the cation, then the lattice energy in the group will remain almost constant. There will not be much change in it. But the hydration energy will definitely decrease on moving down the group as the size increases. And therefore, the solubility will also decrease down the group. Now let's take a look at the various factors that affect the solubility of ionic compounds. The first factor that we are going to discuss is the dielectric constant of a solvent. Now recall that the force of attraction between ions in an ionic compound was given by F is equal to Z1 Z2 E square divided by dr square, where F is the force of attraction, Z1 and Z2 are the charges on the ions, E is the electronic charge, D is the dielectric constant, and R is the interionic distance. Now here D, as we said, is the dielectric constant of the medium. Suppose there are two solvents, say S1 and S2, and their dielectric constants are D1 and D2, such that D1 is greater than D2. Now, from the given formula of the force of attraction, it is evident that greater is the value of dielectric constant, that is D. Smaller is the force of attraction between the ions. So the force of attraction between ions in S1 will be lesser as compared to S2. Consequently, it is easier for ions to break themselves from the lattice and go into the solution in case of S1. Now, water has a high dielectric constant, which is why many ionic compounds are soluble in it. So we can conclude by saying that for a given solute, greater the value of dielectric constant of the given solvent, smaller is the force of attraction between cations and anions, and hence greater is the solubility. The next factor which affects the solubility of ionic compounds is the interionic distance. Now, from the expression of electrostatic force between oppositely charged ions in an ionic compound, it is evident that greater is the interionic distance denoted by R between ions, smaller is the force of attraction between them, and hence greater is the solubility in the given solvent. Let's take the example of halides of lithium. Lithium fluoride, lithium chloride, lithium bromide, and lithium iodide. The order of interionic distance for these compounds is lithium fluoride, which is less than lithium chloride, which is less than lithium bromide, which in turn is less than lithium iodide. Now, since the interionic distance in lithium iodide is greatest, that is R is greatest, F will be smallest as compared to these three compounds, and so the solubility of lithium iodide will be highest. Lithium fluoride solubility is very low, it is almost insoluble. However, if one of the ions is very big, the solubility increases with the decreasing size of other ion. For example, cesium fluoride, cesium chloride, cesium bromide, and cesium iodide. Cesium ion is a very big cation, so the order of solubility will be cesium fluoride more soluble than cesium chloride, which is more soluble than cesium bromide, which in turn is more soluble than cesium iodide. Similarly, in case of a large anion, we can say lithium iodide, sodium iodide, potassium iodide, and cesium iodide. Now again, iodide ion is the largest halide ion. So we can say that lithium iodide is more soluble than sodium iodide, which in turn is more soluble than potassium iodide. and cesium iodide is least soluble. The next factor that we are going to consider is charge on anions. Greater the charge on ions, greater is the force of attraction and hence smaller is the solubility. Since Z1 and Z2 denote the charge on the ions, F will be proportional to Z1 and Z2. Let's take an example. Sodium chloride, magnesium chloride and aluminium chloride. Sodium has a +1 charge, chlorine has -1, magnesium has +2, aluminium has +3 in these ionic compounds. The order of solubility is this: sodium chloride more soluble than magnesium chloride, which in turn is more soluble than aluminium chloride. Here, charge on ions increase as we move from sodium chloride to aluminium chloride, and hence the solubility decreases in the same order, with sodium chloride being the most soluble and aluminium chloride being the least soluble among three. After solubility, we come to another interesting property of ionic compounds, that is their conductivity. Ionic compounds conduct electricity when they are in molten state or they are dissolved in a solution. Conduction is achieved when ions under the influence of electric potential migrate towards electrodes. For example, if electric current is passed through sodium chloride solution, then sodium ion will migrate towards negatively charged cathode. And chloride ion will migrate towards positively charged anode. At cathode, sodium ion will receive one electron to form sodium atom. And at anode, chloride ion will lose one electron to form chlorine atom. This whole process is known as electrolysis. In the solid state, the ions are trapped in lattice structure and are not able to migrate from their fixed positions in the lattice. However, if the crystal lattice has some defects, it can conduct electricity to a small extent. Now suppose there is a defect in the crystal lattice in the form of vacant lattice site. Suppose this is the lattice. And one of them has vacant site. The ion in that place is missing. Then an ion can move from its location in the lattice to this vacant site, thereby creating another vacant site at its original location. For example, if this negative ions move to this vacant site, this particular location will be vacant. This process can continue. So eventually we have a vacant site which we call a hole, which is migrating across the crystal lattice. This process is known as, you must be knowing, semiconduction. And the compounds showing this property are called semiconductors. Now let's begin with the energetics of ionic bond formation. The first term that we are going to discuss is the lattice energy. Recall that lattice energy of an ionic compound or a crystal is defined as the energy evolved when 1 gram molecule is formed from gaseous ions. It is denoted by capital U. So let's take an example. Sodium ion in its gaseous state will combine with gaseous chloride ion to form sodium chloride, which is in its solid ionic crystalline state. Now in this reaction, the energy evolved when 1 mole of sodium chloride is formed is 782 kilojoules. Therefore, we can say that the lattice energy of sodium chloride crystal is 782 kilojoules per mole. There are two ways of calculating lattice energy of a given crystal. The first method is the theoretical method, that is through Bond-Lande equation, and the second method is the experimental method. Let's first discuss the theoretical method of calculating the lattice energy, that is through Bond-Lande equation. Assume that the charges on the ions are Z plus and Z minus. E is the electronic charge and R is the interionic distance. So we can give the electrostatic energy, that is capital E, for 1 mole of the solid ionic substance as capital E is equal to N naught A Z plus Z minus small e square divided by R, where N naught is the Avogadro constant and we know its value is 6.023 into 10 raised to 23 mole. Now in this equation we are assuming that there are more than 2 ions, so the electrostatic energy will depend on their arrangement in the space. This dependence is reflected by a constant called Madelung constant, which is denoted by capital A. This constant has different values depending upon the geometry of the crystal. This table gives us the values of Madelung constant for different crystal structures. Zinc sulfide has 2 types of structures. First is zinc blende and second is wurtzite. For zinc blende structure, the value of A is 1.638. For wurtzite, it is 1.641. For sodium chloride structure, it is 1.747. For cesium chloride, it is 1.762. For rutile, it is 2.408. For fluoride structure, it is 2.519. And for corundum structure, it is 4.171. You must have noticed the negative sign in the expression for electrostatic energy, capital E, which means that energy evolves when a crystal is formed. Also, from the expression of electrostatic energy, it is evident that as the interionic distance decreases, the amount of energy evolved increases. Now, theoretically, when interionic distance becomes 0, an infinite amount of energy should be evolved. Of course, this doesn't happen in practice. But why so? Because there is a small amount of repulsion even between 2 oppositely charged ions, owing to the fact that they have electron clouds surrounding them. This repulsion is negligible when interionic distance, that is small r, is high, but becomes prominent as r decreases. This repulsion force for 1 mole of the ionic substance is given by F is equal to N naught capital B divided by R raised to N, where N is the Avogadro number, B is a constant which depends upon the crystal structure, R is the interionic distance, and small n is again a constant which is known as Bond exponent. This table shows the average values for Bond exponent for different ions. The value of Bond constant, denoted by small n, is 5 for lithium and beryllium ions, 7 for sodium, magnesium, oxide and fluoride ion, 9 for potassium, calcium, sulfide, chloride and cuprous ion, 10 for rubidium, bromide and argentus or silver ion, and 12 for cesium iodide and orris or gold ion. So the total energy holding the lattice together can be given as the sum of energy of attraction and energy of repulsion. The equilibrium distance between ions is achieved when du divided by dr is 0. Let us assume that the equilibrium happens when the distance r is equal to r naught. So we can write du divided by dr is equal to N naught A Z plus Z minus E square divided by R naught square minus small n N naught B divided by R naught raised to N plus 1. If we equate this equation to 0 and rearrange it, then we can obtain the value of capital B, which comes out to be A Z plus Z minus E square R naught N minus 1 divided by N. Now, if we substitute the value of B in the expression of lattice energy, we obtain lattice energy, that is U equal to this quantity. If we write this equation in terms of SI units, we get U is equal to minus N naught A Z plus Z minus E square divided by 4 epsilon naught R naught raised to 1 minus 1 by N. Epsilon is the permittivity of the medium Epsilon naught is the permittivity of free space and its value is 8.854 into 10 raised to minus 12 farads per meter. Born-Haber cycle can be used to calculate lattice energy of a crystal as well. The cycle was devised by Born and Haber in 1919 and it relates the lattice energy of a crystal to other thermochemical data. Consider sodium chloride for example. We know that the lattice energy is the energy evolved when gaseous ions, that is, sodium ion and chloride ion in this case, come together to form 1 mole of the solid ionic compound, that is sodium chloride. Standard state of sodium is solid and for chlorine it is gas. So initially we have solid sodium and gaseous chlorine, which ultimately form the ionic compound sodium chloride, which is again a solid. This equation expresses this phenomenon for the formation of 1 mole of sodium chloride. The change of enthalpy in this reaction will be equal to the enthalpy of formation. The formation of the sodium chloride that we showed through this single step actually consists of various intermediate steps. As we discussed that solid sodium and half of chlorine molecule combine to form sodium chloride, which is again a solid, and the enthalpy of this reaction is equal to the enthalpy of formation of sodium chloride. Let's see what all intermediate steps are involved in this reaction. So let's start with solid sodium atom and half of gaseous chlorine molecule. First of all, the solid sodium atom is converted into gaseous sodium atom. The enthalpy of this reaction is equal to the enthalpy of sublimation of sodium. Then the gaseous sodium atom is converted into sodium ion. The enthalpy of this reaction is equal to the ionization potential or ionization energy of sodium. Then the chlorine gas molecule dissociates into chlorine atom. A chlorine molecule is composed of 2 chlorine atoms. We all know that. The enthalpy of this reaction will be equal to the enthalpy of dissociation of chlorine. Since we start with half of chlorine molecule, the enthalpy of dissociation is also mentioned as half. Now we have in our hands sodium ion and chlorine atom. Now this chlorine atom is converted into a chloride ion by gaining an electron. The enthalpy of this reaction, that is conversion of a neutral chlorine atom into a negatively charged chloride ion, is equal to the electron affinity of chlorine. Sodium ion and chloride ion, which are oppositely charged, will combine to form sodium chloride. These ions were in their gaseous state and the product, that is sodium chloride, formed is in a solid ionic compound. The enthalpy of this reaction will be equal to the lattice energy of sodium chloride. So if we follow all the intermediate steps one by one, then in the first step, the sodium atom is converted to gaseous state. This change requires energy, which is provided by the enthalpy of sublimation. Note that the sublimation is defined as the direct conversion of a solid into a gas at constant temperature and pressure. And the enthalpy of sublimation is the change in enthalpy, which occurs when 1 mole of a substance sublimes at a specified temperature and pressure. In the second step, gaseous sodium atom is converted to gaseous sodium ion. The ionization energy or the ionization potential energy is required for this process. We can define the ionization energy as the energy required to remove an electron from the neutral atom. In the fourth step, chlorine atom is converted into a chloride ion by accepting an electron. The energy required for this process is equal to the electron affinity of chlorine. The electron affinity of an element can be defined as the energy given off when a neutral atom in the gas phase gains an extra electron to form a negatively charged ion. In the fifth step, gaseous ions, that is sodium ion and chloride ion, combine to form solid sodium chloride crystal. and the energy evolved in this step is known as lattice energy. As we discussed earlier, lattice energy is the energy evolved when gaseous ions combine together to form 1 mole of the solid ionic compound. According to Haber's law, the overall energy change in a process depends only on the initial and final states and not on the route taken. So we can say that the enthalpy of formation that we discussed in the very first equation is the sum total of the various enthalpies involved in the intermediate states. I hope you remember this was the first equation we discussed, in which a solid sodium atom and chlorine in its gaseous state combine to form sodium chloride crystals. And the enthalpy change in this reaction is the enthalpy of formation. So, as per Haber's law, enthalpy of formation is the sum total of enthalpy of sublimation of sodium, ionization energy of sodium, half of the dissociation enthalpy of chlorine, electron affinity of chlorine, and lattice energy of sodium chloride. Now let's try to solve few simple questions based on the concepts that we have just discussed in this chapter. The first question: for 2 ionic solids, calcium oxide and potassium iodide, which will have higher lattice energy? Let's recall that according to Coulomb's law, the force of attraction between ions is directly proportional to the charges on the ions. In case of calcium oxide, the charges on the ions are +2 and -2, and in case of potassium iodide, the charges are +1 on potassium ion and -1 on iodide ion. So it's pretty simple that the force of attraction between the ions of calcium and oxygen, that is calcium ion and oxide ion, will be much greater in the lattice of calcium oxide, and therefore it is going to have higher lattice energy. It is also supported by the experimental facts which show that the lattice energy of calcium oxide is much higher than that of potassium iodide. Second question: which of the following choices will not favor the formation of an ionic compound AB? First is high ionization energy of A, second is high electron affinity of B, C is high lattice energy of AB. If we can recall the various intermediate steps we discussed in the Bond-Haber cycle depicting the formation of sodium chloride, ionization energy was the energy that was to be supplied when the atom A was converted into a positive ion, A+. Similarly, electron affinity of B was the energy released when B gained an electron to form a negatively charged ion. Lattice energy was also the energy released when A+ ion and B- ion combined to form the ionic compound AB in its solid state. A+ and B- are in their gaseous states. So ionization energy is the energy which is to be supplied among these three. In case ionization energy is very high, then the energy barrier posed may be so high that it may not be overcome by the sum of the energy released in the other intermediate steps. In that case, ionic compound AB may not be formed. So our answer will be A, that is high ionization energy of A. Third question: which of the following solvents is best for ionic compounds? The number mentioned in the parenthesis depicts the dielectric constant of that solvent. The 4 solvents given are acetic acid with dielectric constant 6.2, acetone with dielectric constant 21, formic acid with dielectric constant 58, and chloroform with dielectric constant 4.81. By Coulomb's law, the force of attraction between the ions was inversely proportional to the dielectric constant of the medium. We studied it while discussing the solubility of ionic compounds. So, higher the dielectric constant of the solvent, lower will be the force of attraction between the ions, and much easier will be the breaking away of the ions into the solvent. That is, their solubility will be high. So that solvent in which the ionic compounds are most soluble should be such in which its ions feel the least amount of attraction. For that, the dielectric constant will have highest possible value. In the given solvents, formic acid has the highest dielectric constant. So among these four solvents, formic acid will be most suitable for dissolving ionic compounds. Next question. Reaction enthalpy of which of the following reactions will be equal to the lattice energy of sodium chloride? Now, if we remember the definition of lattice energy was the energy involved when gaseous ions combined to form 1 mole of solid ionic compound. Among the given choices, choice D says that gaseous sodium ion combines with gaseous chloride ion to form solid sodium chloride. So the enthalpy of this reaction will be equal to the lattice energy of sodium chloride. So our answer is D.